percentage error. Absolute, relative and percentage error. These three errors are used for the calculation purpose, and these can be defined mathematically. This is very important thing. Absolute error, relative error and percentage error can be defined mathematically. So, the definition for the absolute error is true value minus approximate value, its module. This is absolute error is equal to true value minus approximate value, that is true value is x and approximate value is x prime. So, absolute error is the absolute value of the error, simply error. Next we come to the relative error. It is defined as absolute error divided by true value. Absolute error is x minus x prime while true value is x. So, absolute error is x minus x prime and true value is x. So, relative error is equal to x minus x prime divided by x, its modulus. This is called modulus. So, now we come to the numerical portion about absolute error and relative error. First we study the absolute error. The difference between the measured value and true value, it is referred to as absolute error. Assume that the analysis of an iron ore by some method gave 11.1%, while its true value is 12%. So, the absolute error is true value minus approximate value. True value is 12.1% and approximate is 11.1. So, the absolute error is minus 1.0%. Next, what is the relative error? Relative error is the, sorry, here it is not percentage. Relative error is absolute error upon true value. Absolute is minus 1.0 and true value is 12.1. This is percentage error, minus 8.3%. This is percentage error. Next we come to the relative accuracy. The percentage of the quotient of the observed result to the true value. So, the observed is like 11.1 while the true value is 12.1. So, the relative accuracy is 11.1 divided by 12.1 into 100. This is 91.7%. This is relative accuracy here. Next we come to the percentage error. Percentage error is noted by EP is equal to 100 into ER. This is in percentage. So, ER is relative error. Relative error is equal to absolute value upon absolute error divided by true value, that is 100 into x minus x prime divided by x. This is total percentage error. Next we take another example for the measurement of absolute, relative and percentage error. Suppose 1.414 is used as an approximate to under root 2. Find the absolute, relative and percentage error. We know under 2 is 1.414, 21356. So, the absolute error is equal to true value minus approximate value. True value is 1.414, 21356, while the approximate value is 1.414. So, the absolute error EA is equal to true value 1.414, 21356 minus approximate value is 1.414, which we already used. So, EA is equal to, that is absolute error is equal to 0.000021356. This is absolute error. Next we have to calculate a relative error and percentage error. So, relative error is equal to absolute error divided by true value. Absolute error is 0.000021356 and true value is this one. So upon dividing these two, we will calculate the relative error is 0.151 into 10 raised to power minus 3. This is relative error. Next we have to calculate the percentage error. Percentage error, if we multiply relative error into 100, so we will get percentage error. So the relative error is 0.151 into 10 raised to power minus 3. After multiplying this by 100, we will get 0.151 into 10 raised to power minus 1. This is percentage error. Next we take another example for the absolute error, relative error and percentage error. If we take example that in a measurement the true value of the quantity is 122 mm and its expected value is 120 mm. So the absolute error is true value minus expected value. True value is 122 and expected is 120. So the difference of these two is absolute error. So the absolute error is 122 minus 120, that is 2 mm. This is absolute error. Absolute error has the same units of the quantity. Next is relative error. Relative error is defined as absolute error divided by expected value, or so the relative error is 2 mm upon 120, that is 0.017. A relative error has no units. Third one is percentage error. Percentage error is relative error into 100. Relative error is 0.017 into percentage into 100 is 1.7%. So this is percentage error. Next we divide the error into three classifications. First one is for the consumer purpose, 5 to 10% error is acceptable. How much error is acceptable for us? For the scientific purpose, only 0.1% error is acceptable. But for the engineering purpose, we can a little bit loose, that is 1% error is acceptable. So if for a measurement, if we are taking the measurement of a physical quantity, for the scientific purpose only 0.1% error is acceptable. If there is more than this 0.2, maybe 1, so this is error. This is purely due to systematic error. This may be another reasons, but 0.1% error is acceptable. So we can plus minus, and this type of error we can plus or minus. Now we come to that plus minus point. A range of uncertainty. A range of uncertainty is reported as nominal value plus minus the amount which is called tolerance. So this is reported value. 120 mm plus minus 1 mm. You may study somewhere that this type of reading may be written 120 mm plus minus 1 mm. 120 is nominal value, 1 is tolerance. So 120 minus 1 is 119, 120 plus 1 is 121. So this is range of uncertainty from 119 to 121. Next, if the reported value is 120 mm plus minus 2%, this is nominal value, this is tolerance 2%. So 2% of 120 is 2.4, 120 plus minus 2.4, 120 minus 2.4 is 117.6, 120 plus 2.4 is 122.4. So this is a range of uncertainty. We can vary from 117.6 to 122.4. Next, these are some definitions like accuracy. We defined as degree of exactness or closeness of the measurement compared to the expected value. If our results are near the expected value, then we are accurate. Second definition is resolution. The smallest change in the measurement variable to which an instrument will respond. This is called resolution of the apparatus. Third one is precision, a measure of the consistency or rapidity of the measurement, that is successive readings do not differ. This is precise. Next definition is sensitivity, the ratio of change in output of the instrument to the change in input. If we change some input, then output should change. So this is called sensitivity. Next one is expected value, the design value or the most probable value that expect to obtain. Last one is error, the deviation of true value from the desired value is called error. Now we study accuracy and precision in detail. Like here we take example, measurement precision must be interpreted in the light of measurement accuracy. Let us use a target practice example. This one is target. These are our readings. These 5 are our readings. In this example, these are accurate as well as precise. If these readings are closer to each other, then this is called precise, and if they are closer to this point, then they are called accurate, because actual thing is here. So if all the readings are about this point, then this is called accurate, and if all the readings are closer to each other, then this is called precise. So this example is accurate as well as precise. Now all these readings are not close to each other, that one reading is here, second is here, so these are not precise, but they are closer to this point, closer to this ring, then these are accurate. This reading is accurate, but it is not precise. Third, we come to the point here, these readings are precise because they are closer to each other, but they are not here, so these are not accurate. So this measurement is precise, but it is not accurate. So now I think we can define easily. These data points are scattered, so this is not precise, and these points are away from this point, so this is not accurate. So it is also not precise and not accurate. Precise meaning all the data points should be at one point. Accurate meaning it should be closer to the accurate value. So neither these are precise because the data points are scattered, and not these are closer to the accurate value. So this is accurate and precise. This is not accurate, not precise. This is precise but not accurate, because the actual thing is here, this point measure at this point. So this is precise but not accurate. Next we take the example of given the expected voltage value is 80 volt, the measurement is 79 volt. So we have to calculate absolute error, percentage error, relative accuracy and percentage of accuracy. So absolute error is true value minus expected value. True value is 80 minus 79, so 1 volt. So percentage error is 1 volt divided by 80 into 100, 1.25%. Relative accuracy is 1 minus the relative error, so 0.9875. Percentage of accuracy is A multiplied by 100, so it is 98.75%. Next we come to the limiting error point. The accuracy of measuring instrument is granted with a certain percentage of the full scale reading. For example, a manufacturer may specify the instrument to accurate at plus minus 2% with full scale deflection. So, this is called limiting error. In summary, human error can be due to faulty technique, parallax error can be avoided, anomalous result can be seen on the graph, a random error can be reduced by taking many readings, so then calculating the average or mean. Systematic error including zero error will cause all your results to be wrong. Thank you.